This problem, we have a three-phase 4-wire star connected system and the neutral has become open circuited. Okay, so we've got no neutral, we've got unbalanced loads in each phases, and the voltage is measured 270 across the A phase, 300 and 165 across the B phase there, with line voltages still at 400. So our exercise is to use a phasor diagram to indicate line voltages, phase voltages, because the start point will shift due to the broken neutral, calculated phase currents, and load start point to earth potential difference, or the earth potential rise that occurs on the earthing system due to the open circuit neutral of the supply there. So phasor diagram, I guess we could get some information before we go and start that. So we've got a line voltage of 400 volts, of course. The phase voltage VA is 270 volts. VB, we're seeing at 165 volts. VC is 300 volts. Calculated phase currents, so we can do a quick calculation on them. So IA phase would be the V phase, of course, over the impedance of the phase ZA. So we've got 270 volts there over 10 ohms, obviously 27 amps for the A phase. B has got 165 volts across 8 ohms. So we end up with a current there of 20.6 amps, and IC 300 volts divided by 12 ohms impedance there, giving us a current of IB 20.6, 25 amps. There we are. Okay, so we can work out, we want to use a phasor diagram. We're asked to do that to indicate all these values on the phasor. So we'll get that underway here. So always start, as I say, with your three-phase phasor voltage reference. So we'll have to make up a scale here now for the voltages, because they've been shifted and moved. Our highest voltage would be 300 volts. So I might say that 1 centimetre is equal to, let's say, 30 volts. That'd make that 300 volt 10 centimetres long. So we'll just start but with our 230 volts, so which would be all our balanced system, you know. So if we had VA there at 230 volts, 120 degrees down here, we'd have VB, and 120 degrees up there we'd have VC. So they're all in there representing phase voltages. Maybe if it was 230 volts, if it was nicely balanced, everything would be good, but it's not. We've got an open circuit neutral. So we saw in the diagram the line voltage 400 volts, which are those 2 points as we've seen in previous phases between there. So line voltage remains the same. So V line A to B would be your 400 volts, of course. Your line voltage B to C, V line B to C 400 volts, and C to A V line C to A also 400 volts. Because the open circuit neutral, this start point we would normally have is now shifted. We're seeing these voltages imposed on each phase, 270 on the A phase, 160 on the B, and 300 on the C phase. So that means this star point has shifted. So from that point there, we're measuring on the A phase 270 volts. So I've got to set the compass at the scale of 1 centimetre of 30 volts, so 9 through 270 volts. Come through to 9 centimetres there, and come to the end, the tip of VA, and you can scribe an arc. Okay, so that's somewhere around that arc is the voltage imposed on the A phase. The B phase was 165, so on our scale, if we set our compass to 5.5 centimetres, equal to 165 volts, come to the end of the B phase and scribe an arc. See two arcs intersecting there. And just to prove it, the C phase is at 300 volts, which would be 10 centimetres long. We come to the end of the C phase, scribe an arc, and it intersects the other two arcs at that point, you can see, just in there. So therefore the distance between there and there voltage-wise as the voltage that's imposed on the earthing system due to the open circuit neutral. Okay, so if we measure that, that's 2.5 times 30, which is equal to what is it, 75 volts. So voltage neutral to earth is equal to 75 volts. Is that it? I think that's all I wanted. The load star point to earth, the potential difference. So I suppose it's star point to earth, not neutral, but that's okay. You can still see how you've got 75 volts that's been imposed on that system. I'll just dot those in, those voltages, say between there and there. That's the new voltage that we scribe the arcs to. And you can see a bit clearer how the star point actually shifts. Okay, so if we've got that, then the currents in each of those phases are also in phase with those voltages, but no power factor given. We've got 27 amps as our largest there, so we'll come up with a scale for current. 27, let's say 1 centimetre is equal to 4.5 amps. Okay, so the A phase current, the 27 divided by 4.5 is going to be 6 centimetres long. Right there. I'll do that in a different colour. Six centimetres long, that'll be the IA to that point. IB 20.6 is 4.5, 4.6 long. 4.6 is the current in IB. IB 4.6, oh sorry, what was it, 20.6 amps. IA was 27 amps and IC was 25, which is 5.5, 5.6 long up along that C phase voltage. Okay, IC, which was 25 amps. Yeah, so that's your phasor showing the neutral to earth voltage, star point voltage, 75 volts, and 3 currents in each of the lines